Well, thank you for the leading clap. I wasn't expecting that, actually, especially in the post-lunch slump, which I'm sure everybody's in. So if you just want to sort of nap or fall asleep, I won't be offended, so I'll put that out as a disclaimer. So we're going to talk about the evaluating fairness in machine learning. I just want to start by saying that we're going to talk about an extremely limited definition of fairness. You know, I'm not an expert in ethics or in social sciences. My background is engineering and machine learning, so people have been thinking about biases in data and the fairness of decision-making for a far longer time than I have, and it's a very mature field. But fairness in machine learning is a very interdisciplinary field, and a lot of the papers have really only been arising in the last couple of years. So I'm going to talk about it specifically in a machine learning context, and in that context, it's where we have what we call protected attributes. So these are things that we know about people, which describes a group that they belong to. So people are in different subpopulations, and this subpopulation is described by some attribute. And the idea is that people within each of those groups should be treated fairly, because we know a priori that it doesn't affect the output of the system. There's also, in this case, no consideration of any historical biases towards members of each group or societal structures that already discriminate against them. Because if before you build your decision learning system or your decision-making system, people are already discriminated against in some other way, then there are often some policy levers we might want to pull in order to negate historical biases. So we're not going to talk about that. We're talking about a very limited context where we know which groups people belong to, and we want to know how do we make a decision in a fair way. Okay, there's a broad spectrum, of course, of decision-making, and the unfairness can arise at both ends of the spectrum. So even fully human decision making can, of course, be biased, and so can automated decision making. And I suppose one benefit of doing it in an automated way is that perhaps we can at least probe a little more than we can probe somebody's brain into how the decisions are being made. So maybe it could be more fair, maybe not. I think we'll find out, but there's a lot of issues. And one of the outcomes will be that the most important thing is that we're at least evaluating how fair we're being when we're making an automated decision. And we could also lie anywhere in the spectrum here. So we can use perhaps producing a score which enables people to make decisions, or we at least put in some prior distributions based on expert knowledge. And those could be biased as well. So there's biases from the human side and biases on the machine learning side. And the biases can come in anywhere in the machine learning pipeline, okay? I mean, these are very core steps. But in general, we start with data collection, which we're not going to talk about really today. And this is actually a really interesting collection of essays. I've put that far too small. But it's called Raw Data is an Oxymoron. And it's a bunch of historical studies showing that really data is never neutral. Data is a sort of a cultural concept and something that we all share. And the idea is that it's really impossible to collect that in a way that's purely raw, so purely unbiased. And so we should really start considering at the very beginning, are we collecting data in an unbiased way, and perhaps dropping data that's going to skew our decision-making or account for things or biases that we know are in the data, if they can't be helped. And then a very cool area, and I find really interesting, is the area of algorithm design. It is extremely cool, but we're not going to talk about it today. And this is how can we train our models on the data in order to minimize fairness. So how can we structure the models, and how can we design them from the ground up so they have fairness baked into them, whatever definition of fairness is, and we'll come on to that. And there's another really interesting paper, which is on arXiv, which is called Avoiding Discrimination Through Causal Reasoning. And this is a really interesting paper where they use Bayesian models to introduce causal relationships, so we can explicitly say this protected attribute does not affect the output, and these ones do. And by having that as a hard constraint in the system, then we can essentially train the model to learn that this group membership does not affect the output. And again, that's algorithm design, and we're not going to talk about that too much. But today we're going to focus more on decision-making. So the context is we have a trained machine learning algorithm. It's maybe a black box, and it just gives us ones or zeros, or it gives us a score. Or equivalently, we have a human, right? It's the same thing. They sit there. We can't probe their brain, but they just deliver some sort of decision to us when we ask for it. So, for example, a judge. And we want to understand how can we analyze the fairness of that decision-making process, or in the context of machine learning, how can we use the outputs of the learned system in order to make fair decisions? Okay, so we'll start with evaluating fairness, because we haven't really defined what fairness is. So a common example is a police stop and search. So here we have Chief Wiggum and Homer, and they're driving around, and they're going to stop people who they believe to be unlawful. So they're going to go and do a search, and then if they have some contraband on them, then they get arrested. And they want to minimize, of course, stopping people who don't have anything on them, because that can be a traumatic experience for somebody. But they also don't want to miss people with contraband that are out in Springfield, because then that's also a negative thing for the public, to have unlawful citizens around. And they're taking two different approaches. So Chief Wiggum has, for some reason, extremely suspicious eyes, and maybe we expect that. And he's looking around and he's trying to determine, just using his natural functions, his cognitive faculties, who he thinks is unlawful, and therefore who he should stop. Homer, on the other hand, I have no idea if this is actually what was happening in this scene in The Simpsons. I haven't seen this episode. Homer's on a laptop, and maybe he's actually inputting features that they see into a deterministic machine learning system. So it's pre-trained, and he just gets back, for example, like a probability. So based on things I typed in, there's a 70% chance that this person is unlawful. Now, it is, of course, in everyone's interest that as they drive around Springfield and Shelbyville, I think is that the other town, in Shelbyville, in The Simpsons, they want to treat people from those two towns equally, because they have no reason to believe that just because you identify as being from Shelbyville that you're more likely to commit a crime. So I'm going to try some audience participation, but as I said, it is post-lunch. So I understand this could fail horribly. So maybe I'll just ask people up front, how would you go about stopping people to ensure that you don't bias against people from Shelbyville and Springfield? Ignoring the fact that in The Simpsons they probably would definitely be biased towards people from Shelbyville. Does anyone have an idea? Yeah.
Randomize your process.
Yeah, so just like completely randomized search, maybe like stop every 10th person. Yeah, that's a good one. Anyone have any more? Or maybe that's the first one that comes to mind. Yeah.
Spend proportionate amounts of time in the two towns.
Yes, that's another very good one. And so one problem with the randomized search is that if you're trying to do that in sort of blind to the protected attributes, we say, oh, we didn't care what we're doing, we're just going to stop every 10th person. Then maybe they end up driving around, you're right, like Springfield more than Shelbyville, so they happen to be stopping people from Springfield way more often. And so the approach certainly seems biased, and actually will be biased and unfair towards people from both, because they'll miss criminals or unlawful people in Shelbyville, and they'll maybe stopping people more often than they should in Springfield. So yeah, you could control for that. Anyone have anything? Yeah?
What if you take a first random person, and the second next person, you make sure it's from the other town, and then you iterate like this. So it's not random,
Yep.
but in the end, you've sampled from both distributions.
Oh, okay, yeah, so you stop someone from Springfield, then if you stop the next person and they say I'm from Springfield, you say, oh, don't worry. And then we go to the next one, right?
Yeah, or you make sure that you
Yeah, the proportions are right.
like, let's say they've got different hats, and you know which ones are which ones.
Yeah, so maybe they wear like I Heart Springfield hats. Yeah, that's a good idea. So in these kind of scenarios, and we'll go on in a minute to evaluate these, and all of these different options will come up. There are lots of different ways where we get some black box scores, and we have to make a decision that affects people's lives. So, for example, loan approval, insurance premiums. So this is particularly relevant to my day-to-day work at Slitora. I'll come to that briefly at the end. Of course, there's going to be a hiring slide. And, for example, detention rates. So how do you decide who to arrest? Or there are scores that assist judges. That actually exists. And also the reoffending rate. Has anyone heard of the COMPAS score? This was very newsworthy. Yeah, a few people. So this is a score that was developed in America, which is a black box score, which helps judges to evaluate whether a criminal is likely to reoffend, and therefore whether they should release them early or whether they should stay in. So these are really black box models that are affecting people's lives. And in any case, when there's any risk score or probability and we have to make a decision, we need to be quite careful about how we're applying it. Okay, so the first idea, which maybe the randomized stopping would involve, is the idea of fairness through unawareness. And actually, I think like a huge proportion of machine learning actually just comes under this banner. So this is, we don't use any protected attributes. And as long as we don't put them into the system, then we're not really being inherently unfair. And we do accept that maybe there'll be some correlating variables, but we say, oh, but that's just how the data is, and we'll build it. But of course, that doesn't really work, because you end up learning proxies for the protected variable, which mean you're still being unfair. So this was the example I came up with. It was intuitive to me, but I don't know if it is to others. And I got the idea from this paper on counterfactual fairness, which you should definitely read. It's really interesting. So the idea is that we believe there's some latent variable, so we can't observe this, which is the criminality of a person. And that criminality, of course, directly affects whether they're being unlawful. So in the stop and search, we believe that some people that we're driving past in Springfield really have some level of criminality to them, which correlates with whether or not they're going to be carrying some contraband. And it also so happens, for some reason, that they prefer McDonald's Quarter Pounders with cheese over Krusty Burgers with cheese. And that's OK. Criminals can do that if they like. But it also so happens that people from Shelbyville prefer McDonald's over Krusty Burgers. And so you can see, in this case, we don't use this feature. This is the protected feature, whether people are from Shelbyville or Springfield. So we decide to ignore it. But we do observe, because we're trying to ingest like as much data as we can, people's preference for Krusty Burgers over McDonald's. And you can see from here that if we regress or we learn, try to learn unlawfulness through this latent variable, through whether people prefer Krusty Burgers or McDonald's, then you're going to inherently be learning this highly correlated variable as well. So you're going to end up discriminating for people against Shelbyville. I think it is actually proved in this paper that if this is linear regression, then this actually ends up being a fair way to do things. But in any nonlinear setting, then you're going to learn, you're essentially going to learn to be biased. And in this case, this is quite a positive link. So the idea that people prefer Krusty Burgers is kind of seems quite innocuous. But there are, of course, other more baked-in things in society. For perhaps if you're born into a certain area and there's less opportunity for you, then perhaps that means you have attributes about you when you're older that aren't related to these protected attributes, but that we think are kind of safe to correlate on. So, for example, in credit risk, of course, income will directly relate to whether or not you can pay back your loan. But of course, we accept that some people are born into a situation where their income will be inherently lower. And so that's a very similar setup to what we have here, but it is, of course, quite a negative situation. OK, so we'll come on to some definitions of fairness. I think this is the one that cropped up the most between people, and this is what's called demographic parity. So here we have two populations. One is orange and one is blue. This is a minority population, the majority, but it doesn't really matter. The important thing is that the distribution of people, the predicted distribution is the same for both classes, for both groups. So for example, in the police stop and search, this is the people that we stop, i.e. we predicted that they would be unlawful. And whether or not they actually turned out to be or not, the idea is that we stop the same number of people. And that seems quite fair. I think that's what came from over here. So stop people representatively. Or similar to driving around Springfield and Shelbyville. It's the same idea. We're trying to get an equal proportion in both. And actually, this has been used in police stop and search, and it's called benchmark tests. So they're just making sure that you're not stopping proportionally more from one group, members of one group, than members of another group. But it has problems. Of course, the fundamental problem is if the underlying base rates in each of the groups really are different. So in this case, in the orange class, so C1 is like a true positive, and, whether the true label is 1 and the true label is 0. And things to the right of this line we predicted as 1 and predicted as 0. So again, if we think about the stop and search case, these are people that really had contraband on them, people that really didn't have contraband on them. So more often, people are being unlawful in this first group than in the second group. So I think we can see here that it might not be fair, for example, for this group, because half of the people that are stopped are not criminals. So for them, their utility is very low. Like, that's a very unpleasant experience for them, potentially. And likewise, if you look on this side, out of the people that were missed, half of them were criminals. So criminals seem to be getting away with it more often. And so if we think about this in standard notation that you could apply to any machine learning algorithm, it's the idea that the probability of being in class 1 is essentially the same no matter which group you are. And this is a binary classification problem. We'll restrict the discussion to that. So that's the idea of a benchmark test, that you're equally as likely, for example, to give a loan to every person in each group, or you're equally likely to detain somebody in each group. But if the underlying base rates are different, then it doesn't really work out. So the next thing we can try is we can condition on the true outcome. So this is essentially the false positive and false negative rates. So in this case, if you look at the total number in both groups, if you look at the total number of people that are being unlawful, in both cases, we've managed to catch half of the criminals. So that wasn't true in the last case, where we were catching a larger proportion of the blue criminals than the orange criminals. So can you see how that might be unfair? And you can see how this chimes with people's experience. That they say, oh, well, you know, more criminals, proportionally, are getting away with it in the other group. And we can also have that our false positive rate, you could also make sure that that's the same, which actually it isn't in this case. So this is, of all of the negatives, what proportion are we predicting that they're positive? So in this case, how many people are we stopping that really aren't being unlawful? And in this case, you can see that, nobody unlawful in this group was being stopped, which is good. But here, a third of unlawful people are being stopped. But if you balance both of those, then that can work quite nicely. So this is conditioning on the true outcome. So are the error rates the same for people who really are criminals, and are error rates the same for people who really aren't criminals in both groups? Does that make sense? I still get confused all the time now with, even after many years, with true positive, false positive, true negative, false negative. So if I ever get them mixed up or anything, just shoot up a hand or abuse me or shout. OK. The other thing we can do is condition on the predicted outcome. So this is the idea that of the people that we predicted to be criminals, was the proportion the same over each group? So for example, what have I done here? Oh, so here you can see that of people we predicted, so let's just look on the right-hand side, that 2/3 of the time we were correct. And that's the same for both groups. So did you realize that's different to beforehand, where we're saying the proportion of true criminals being stopped in each group is the same. And here is the proportion of predicted criminals in each group are the same. And both of these could be seen as unfair. Sorry, both of these are fairness criteria. And if you don't match either of them, then you can be unfair in different ways. So here, the criticism would be, well, more criminals are getting away with it in group A than in group B. And here the criticism is that you're stopping people more often in group A than in group B, who really are criminals. These, in fact, all of these criteria and these fairness criteria can be entirely written in terms of the false positives, false negatives, and true negatives. And if you go to this paper, which came out fairly recently, you get a whole list of all of these fairness criteria in a coherent notation, which I find really useful because these different metrics for fairness often have very different names or conflicting names, or they use completely different notation in the literature. So this is a very good way, I found, to get everything down, get the notation set. And so I would recommend taking a look at this. Can everyone read that? It says, fairness in criminal justice risk assessments, the state of the art. But unfortunately, there is inherently an impossibility condition. So this is what we're going to talk about. So imagine here, this is the outputs for lots of people in the population, and I've colored the two groups again, orange and blue, and they're ranked from the machine learning or the human decision maker's probability of being in the positive class. So in this case, the probability that they're carrying contraband. So on this side, we're pretty sure that they're not going to be carrying anything, whereas over here, we're 100% sure that they've got something. And so you can see that the distribution is pretty messy, but there's definitely more true criminals. So remember, the black means that they're really carrying contraband, and the hollow circle means they're really not carrying contraband. So it does seem that we're doing kind of well on both groups. So let's think about, firstly, the benchmark test. So, oh no, this isn't a benchmark test. See, I'm already getting confused. This is just equal thresholding, so fairness through unawareness. And we just say, OK, well, we don't care what group people are in, but as long as we predict that there's like over a 70% chance that they're carrying something, then we'll stop them. I feel like that would actually be quite high. Maybe it's more like if it's over 10%, you want to stop them. I'm not sure. But you can see that this is unfair by a number of metrics. Many more are getting stopped proportionally. Or maybe those proportions are quite good. But you can see here that half of the people stopped here weren't criminals, and here everybody was. You can also see that more criminals are getting away with it in this group. So it doesn't work, but we've already covered that. And you could put that slider anywhere, and you're going to have this problem. So this is the thresholding. So again, maybe these are all the people we stop, and those aren't. And we, again, have these kind of different distributions of false positive rates and false negative rates. So one thing we can do is we could actually apply different thresholds to each group. Now, if you realize the fundamental difference is that we now have to know the membership of each person within the group. So now we've moved away from fairness through unawareness. And we have to actually account for this protected variable, which goes against a lot of what the intuition is, which is like, if we don't want to be biased, we just shouldn't include those things in the model. But here we need to know the groups. And again, they don't actually have to be inputs to the model, but we need to at least know when we do the evaluation of the decision making, we need to know which group people are in. And here, we've got the case that half of the people being stopped, no, that looks like proportion of criminals being stopped is the same. So this is the benchmark test. So you've had the same proportion of people on the right as you do on the left. So we're stopping people proportionately fairly, which is, again, what came from over here. We should just walk around, and we should make sure that people are stopped at the same rate in each of them. But the problem is that here we only got half the people we predicted are having a quite horrible time because they weren't really criminals, whereas here many people were stopped. So we could adjust the sliders again, and you can see, I mean, I won't go through every example, but you can see that we can move these thresholds, and you can change the false positive and false negative rate. But much like when you have your ROC curve, for example, and you're changing the threshold. But in this case, it's kind of like you have two ROC curves, one for each population, and you can move those thresholds, and you're adjusting the rates for both. And you either want to get the false positive rates to match or the false negative rates to match, or ideally everything. And so it's perfectly fair if all of those fairness criteria that we've spoken about are true. But the impossibility condition, unfortunately, says that if the data is not separable, which we had here, so we can't draw one line that clearly separates true criminals from truly not criminals. If the data is not separable and the base rates within each group are different, so the true number of criminals in each group are different, then we cannot be fair on errors conditioned on true outcomes and errors conditioned on predicted outcomes. So, in other words, we can't be fair both in the proportion of criminals in each group that are stopped and the proportion of people that we stop that end up being criminals. And if you think about it, one of those is more to do with the individual who's being stopped, and one is more to do with society. And this is in this paper, and it's mathematically proven, inherent trade-offs in the fair determination of risk scores. So if you take a look at that, and you can basically see that even if we know the probability, if we calibrated our classifier, so always got the probability correct for each group, so if we say, oh, this person's 50% likely to be a criminal, and they really are 50% likely to be a criminal, we'll actually end up stopping people at the wrong rates in each group. This is a difficult pill to swallow, is how they phrase it in the paper, and I think that's true. So in summary, how can we achieve fairness? Well, we cannot achieve fairness in both the predictions and the outcomes. It's rarely fair to use the same threshold for everybody, but in a way that's also a policy and a debate point. We need to choose one metric, and that metric depends a lot on the domain knowledge. So you really need to know, for a given example, whether or not it's worse for people to be stopped when they're not really criminals, or whether the proportion of criminals being stopped is the biggest problem. And this is, again, this is a very limited definition of fairness, and it's only one example. But in the case of, for example, loan applications, maybe one outcome is not as bad as another. So commonly with loan applications, people would say it's more important that those who need a loan are able to get it than those who then just making sure that the right proportion of people in each group are getting a loan. So it depends on the utility of the individuals. And so you really need to have some domain knowledge. So in summary, measure all the metrics, which is easy in machine learning, but not so easy for humans. So I'm just really going to quickly talk about a very interesting paper, which was to do with police stopping procedures in North Carolina. And I took the stop and search data for the UK, and I tried to apply the same model. I did apply the same model. To get an idea of whether there's biases in the way that people are stopped and searched in the UK. And so the procedure is this. A policeman is driving along in the car, and they observe the probability of somebody being unlawful. Now, if you think about the data we have, we only know the proportion of people stopped because the police write down, we've stopped someone, and we can normalize that by the demographic in a given area. So if we know there's far more people of Group A than Group B, then we can make sure that that benchmark test is correct, that the right proportion of people are being stopped. And we can also observe the results of the search, because they note down if nothing was found and if something was found. So we can make sure, we can check that that outcome distribution is also the same. So the procedure in the model is this, and there's a lot of assumptions baked into it, but that the people walking on the street have a probability of being unlawful, and police officers have a threshold which can vary for different groups. So, for example, it could be ethnicity or gender, but we allow that threshold to vary for each group, but it's constant throughout that group. So perhaps they stop males at a different threshold than they stop females. So they observe the probability, and if the probability of that person being unlawful is below the threshold, then they're not stopped. And if it's observed to be above the threshold, then it is stopped. Now notice here that these are all latent variables, so we don't actually know the probability that people are unlawful, and we also don't know the threshold. But we're going to try and infer those. Okay, so just quickly on the data that I collected, and I just want to really show that this is extremely limited, and I don't think we should really draw any strong conclusions from the outcome. It's more exploratory, and a reminder that we need to just try and measure these things as much as possible, whether it's human decision-making or machine learning decision-making. So stop and search data exists for the UK. Anybody can download that. And they write record every time they've stopped somebody. And the officer defines the ethnicity. And they also ask the person to define their ethnicity. That correlation can be very interesting. And they also detail like what they were looking for, like why they were stopped, and if they really found something. But we don't have a stop rate, so then you then have to go to the UK census data to get the demographics for each police area. So to figure out whether, in some there's a higher number of one ethnicity living there than perhaps in another area of the UK. And so you need to adjust for that to make sure the stop rates are fair. Because you can't get that from this alone, because you only have the positive examples. So I use the arrest rates data, which already maps the census data to the police areas. So it's very limited. Firstly, the stop rates we have aren't real numbers, because they're relative to the population in the area. And of course, the way policemen do the search is to meet every person in the population and check. But the proportion of the demographics is correct. So it's like an unnormalized variable. So when we see stop rate in a minute, the number itself does not have meaning, but it's the ratio between numbers that's important. Okay, so I'll skip over this quite briefly, but this is what the model looks like. We have the search rate, and this will depend on this probability that we model. That's basically it's essentially a coin flip problem. So you look at someone, and R is the ethnicity or the race. So we let that vary between each. And we're saying, so there's a probability that a person that we stop is unlawful. And then we check whether or not it's above the threshold for that ethnicity from the police officer. And then if it is, we flip a coin, and we stop them with the probability P. And then when we search them, they also turn up something with the probability P. And we place priors on these. I'm not going to go into it in too much detail, because we're running out of time. this is a simplified model that I coded up in PyMC3, and the reason it's simplified is when I was putting this together a couple of days ago, I ran into a limitation, and I thought I would still share the limitation with you. And the problem is that when you do a thresholding problem, it's kind of like a survival analysis. You know, you want to, you know the probability that the person carries contraband has a certain value, and we have a threshold. But you want to essentially do like greater than, so this random variable greater than this random variable, and that gives you a kind of new distribution. I don't know if you know this kind of concept from survival analysis. And there's not a baked-in way to do that in PyMC3. So I ran into, I think I described this as a human limitation, which is that, oh, maybe I didn't put it there. Oh yeah, I couldn't code it in Theano, basically, which is the backend to PyMC3. But given more time, I think you could, so I don't want to berate the developers. But I ended up using PyStam for the full model in the end, because that already has that support in. So shout out to the developers of both of these projects, because they're both incredible for probabilistic programming. But this, in this particular case, was a limitation. So here's a really simplified model of that, which is essentially we have a probability that people will be stopped, and if they're stopped, there's also a separate probability that they're carrying contraband. So in this case, we're modeling the probability that someone's carrying contraband given that they're stopped. So there's no relationship between the two. And so this is what it looks like in aggregate for all of the UK. I also hope to build a hierarchical model, which is training right now. So I'll check if it's finished, but I think it's probably not wise to show the results if they haven't been checked. So this is the stop rate at the top. And again, remember the numbers themselves are not like interpretable, but the difference between them is. And so you can see here that there's a huge delta between the stop rate for blacks being stopped versus whites and mixed. I should also say mixed is a huge outlier because very few police counties allow the officer to use the definition mixed. So most of the counties, the options for a police officer are Asian, black, other, and white. And mixed isn't an option. So that's why down here you have a huge, can you even see that? Oh, no. It's a very flat distribution for mixed. So that one's less reliable. But you can see the stop rates are really different. And so now we're starting to understand why the stop and search in the UK was, of course, again, very newsworthy, and people have had very negative experiences. And now we can start to interpret maybe why that is. And again, I don't want to talk about fairness too much, but certainly it makes sense that people from some populations can clearly feel that they're being treated substantially more unfairly than others, especially given that we don't actually know the proportion, the base rates, the real proportion of criminals in subpopulations. So that's that. And then you have the hit rate here. So this is that given someone was stopped, did they have contraband? So this is like, given that we assigned a positive label, was it really a positive class? So this is what we looked at earlier, which is conditioning on predicted value. And you can see here, I think very interesting, so the Asian population is much lower. And so this suggests that they're probably being stopped, that those from that group are being stopped too often, because when they're stopped, they're less likely to actually have something on them. So this does start suggesting a bias. And again, the mix is like a huge, huge outlier out here. OK, but in this case, we didn't measure the latent variables. This is already in the data. And building the probabilistic model just allowed us to fit not only the expected values, but also get an idea of the robustness of the estimates. So then I moved to PyStam. And so these are the results. So on the left, you have the search rate and hit rate again. But now we have these like latent variables that we've learned. So up here is the threshold that we predicted for the police countrywide to stop people. And here, the inferred probability that people really have contraband. But this is the interesting one. And first of all, I think it's very important to note that these distributions are extremely broad and overlap a lot, and they're very wiggly. So really, I think we need more data to make any conclusions. But we do start to see that there could be some disparity between the subpopulations and the threshold or the standard that police have in order to stop people in each of those groups. And then we'll just zoom in on the bottom one a bit. Oh, I didn't include that. But this is very squished up on the left. But you can actually see that, all in all, the chance of someone being a criminal in each group is extremely similar, especially up here in the tail. Perhaps there's a little more weight, because you can see it drops down here, than others. And so this is the exact underlying problem we saw earlier for the impossibility condition. That if the underlying base rates, and again, we can't observe them perfectly in this scenario, but these are inferred base rates. If these base rates are really different for each subpopulation, then it is impossible to be completely fair by every definition. But I think what's important is that we measure all the different definitions and that we start to understand whether within a given context, for example, police stop and search, if they could have been more fair. And I think here we're starting to see that both the search rate, the hit rate, and the thresholds vary by group, and not in a systematic way. So I think there's definitely a lot of investigation to be had here into whether police are being unfair towards certain ethnicities. No, there are no hierarchical model results. Sorry, everyone, for that. OK, so in conclusion, there are inherent trade-offs if we want to maximize fairness. Firstly, through the different metrics that there are for fairness, but also something we didn't touch on is that there is an intrinsic tension between classifier accuracy and classifier fairness. We have conflicting definitions, and that in general we should apply our domain knowledge in order to determine whether something is truly fair. And as I said, the definition of fairness goes way beyond what we spoke about today. Finally, I think the one thing that I drew from doing this investigation myself was that you should measure everything. Measure it all, measure the false positive rates, measure the proportion at which you're predicting one class or denying people loan applications in any of these contexts, or in the context of insurance, whether we give someone an insurance policy or not. We should be measuring all of those rates to try to determine that for your given domain, whether or not the decision being made is fair. So, yeah, I'll do questions after the hiring. We're hiring at Cytora. So at Cytora, we're developing risk models for the insurance industry and helping them to differentiate more between potential insureds. So if you're interested in machine learning, you're interested in any of these roles, these are senior or junior, we're recruiting for all. So come and speak to me if you're interested in risk modeling. And now I'll take any questions.
We have time for a couple of questions.
Yeah, first at the back, I think. Oh, go on, yeah.
Yeah. Hi, thanks. You mentioned at one point earlier on about learning from a proxy variable isn't a problem in a linear model. I wondered if you could elaborate on that a little bit.
Yeah, actually, I wish I could really elaborate on it. I haven't gone through the paper in much depth, but did you get the reference that I put? Did you note it down? Here. Counterfactual fairness. So this is like a specific definition of fairness that says within a probabilistic model, if you hold all variables the same and flip the protected variable, then the output should definitely not change. And this is the kind of simplest example of that. So it's like if you hold, if you hold all of these and you flip Shelbyville, then that's going to also flip your observed variable. So that by that definition of counterfactual fairness, I think isn't fair. I think the authors are probably going to call me after this and say I'm like completely destroying their work. But the idea is that actually in this very simple example, a linear model happens to satisfy this very specific technical definition of fairness. Yeah, I would definitely read it though, because it's interesting.
My question is this. Is your work related to social choice theory in economics? And I'm thinking in particular of Arrow's impossibility theorem.
So I'm not completely familiar with the second theorem, but I can maybe comment on the first part. And if you told me the definition now, I'm sure I'd probably just stall on the spot and try and come up with an answer.
Arrow's theorem said that here are three characteristics for a voting system. You can't have them all.
Oh, I see. I mean, it sounds like it would be similar, but certainly in economics and social sciences, it's been thought about a lot more. And when I mentioned that there's a trade-off between accuracy and fairness, then if you ascribe some utility, perhaps do false positives or false negatives, they're usually not the same in terms of utility. And also the utility for society, if the accuracy of the classifier is wrong, then there is some social utility theory in choosing the level of fairness that optimizes utility for everybody in society. I'm not sure about Arrow's impossibility theorem. I'm sorry. Cool. We're out of time?
Yeah.
Okay. Thanks, everyone. Thanks very much.